It's indeed a great pleasure and honor for me to give a talk at this conference. So I will be talking about localized states trapped by topological defects in metasurfaces. My main affiliation for many years has been the Australian National University, and on this title slide, I also acknowledge the Australian Research Council, which has been supporting my research positions in Australia, as well as the Centre of Excellence for Transparent Meta-Optical Systems, TMOS, which is also supported by the Australian government. We are located in Canberra, capital of Australia, and here is a picture of the new building of our research school of physics, where we're doing particular photonics research across several departments. One of our key research activities is shaped around optical metasurfaces, planarized nanofabricated materials which interact strongly with light. So they can be viewed as thin layers of subwavelength thickness and structured at subwavelength scales, as shown here, and or alternatively, two-dimensional planarized arrays of resonant particles. Functionalities of metasurfaces are therefore largely based on physics of resonant light scattering, such as Smith theory, and by designing the lattice arrangements and particle shapes, metasurfaces can perform a range of functionalities for radiation control. Planar fabrication of metasurfaces is compatible and quite similar to chip making. They can be used to make optical elements smaller, for instance, to make lenses for light focusing thinner and lighter, and such meta-optics targets a variety of applications in communications and biosensing. However, to make compact personal devices, we would need to pack more functionalities in smaller space, and in general, it requires integration of metasurfaces with diverse materials, such as promising two-dimensional optoelectronic materials. And here the fundamental question remains on how to manipulate light and light matter waves at small footprint most efficiently. This is where topological photonics can potentially step in, because topology offers generic concepts to predict what materials do to waves of any nature. Topological means following some global characteristics, thus less sensitive to local disturbances that could be beneficial for compact integration. Following the guidelines of topology, we can deterministically create the electromagnetic modes of any dimensionality lesser than dimensionality of the system. This could be one-dimensional propagating or zero-dimensional trapped modes. But most importantly, their internal structure enables coupling with materials excitations, such as excitons or phonons in two-dimensional materials. So, but even in this simple vision for hybrid topological platform, perhaps one of the key ingredients, namely zero-dimensional traps for polaritons in open metasurfaces, has been missing, and that was the gap that we addressed in our recent work. Here is the outline of the rest of my talk. I will say a few more words about topology and inspirations that we receive from Dirac-like models in very basic terms. Then I will mention links between topological photonics and other topics very briefly, using examples from our works. And then I will go through our results on topological metasurfaces, preceding topological trapping of polaritons. We prepared recently a review article on this topic for Optical Materials Express, with specific emphasis on radiation control, taking advantage of an open nature of metasurfaces. Before proceeding further, I would like to acknowledge my collaborators across the world, and especially the group of Professor Alex Nikaev from the City University of New York, because today I'm going to show some results of our collaborative work, which includes experimental studies performed in the US. So topology is basically a set of tools developed by mathematicians to classify objects according to whether they can be continuously deformed to each other. Objects from different classes can be characterized by quantized numbers, the so-called topological invariants, and they are sort of global characteristics of the system, such as the number of holes in three-dimensional bodies. They can be defined in different ways. For instance, for closed surfaces, the integral of the curvature over the surface is quantized and can be related to a number of times the normal wraps around a sphere, or alternatively, we can count a number of defects where the tangent vector to the surface goes wrong. On the abstract level, it could be any vector field, and topological classification can be applied to solutions of the wave equations. In particular, we can classify the dispersion branches in the band structures. So in fact, two gapped insulating materials can be topologically distinct depending on the topological invariant of the band. And the critical role in generating the bands with non-trivial topology is played by the band degeneracies. And the simplest one is the Dirac crossing. So the Dirac Hamiltonian acts on the two component spin of wave function. Is an interesting feature is associated with rotation of this spinor because it gives rise to the geometric phase. This is illustrated with this Möbius stripe. So the evolution over the closed path in the parameter space gives rise, effectively flips the sign of the wave function, and we need to go around twice in order to return in phase. To open the band gap in such band structures, we would need, we may introduce the third Pauli matrix term, the so-called mass term, and the domain wall created by the interface between two topologically dissimilar materials, basically by the mass inversion, by the change of the sign of the mass. It can support the topological H states with linear-like dispersion crossing the band gap. They appear to withstand perturbations of the system because their origin is deeply rooted in topology of bulk bands. The general form of the Hamiltonian can be decomposed in Pauli matrices, and such Hamiltonians can be generated in two-dimensional lattices with pseudo-spin degrees of freedom. Just an illustrative example here corresponds to 2D lattice, to a square lattice with two orbitals per side and specific lattice coupling arrangements. So this lattice can support two topological phases, trivial, non-trivial, depending on parameters. And topology would effectively count a number of defects or number of abstract holes in the eigenwave function, so that we cannot define gauge continuously over the whole Brillouin zone, or we can illustrate topology in the reciprocal space by different means, as shown here on the left. So we can plot the spin texture, where in the non-trivial phase we can observe Hedgehog's fermion. Then we can map the Brillouin zone towards the sphere, or we can just plot a polarization angle. All these pictures will clearly distinguish trivial and non-trivial phases. And interestingly, we recently pointed out that similar non-trivial three-dimensional vector fields, such as fermions, can be generated by simple waterways, by simple linear interference of surface waterways. So the first review on topological photonics itself appeared in 2014, and this journal cover on the left illustrates such electromagnetic wave which propagates along the edge of two-dimensional photonic crystal and bypasses the defect almost without back reflection. So here, time reversal symmetry is explicitly broken by the external magnetic field, but the with preserved time reversal symmetry would be preferential in optics because magneto-optical response is weak. In the latter case, suppression of backscattering is rather conditional, depending on the symmetry of the field or geometry or types of defect, but still topology gives us a significant guidance scheme how to design waveguides and resonators in photonics. So we can create waveguides based on the domain walls, or we can design resonators, cavities, using the enclosed domain walls, or more complicated mass winding, or high-order topological phases which can confine light to the corners. And of course, optical nonlinearities can give rise to plethora of interesting effects in topological photonic systems. We describe them in our review article, summarizing developments up to 2020. Since then, a lot of new experimental observations appeared of topological solitons and frequency comps, but from our own perspective, we studied nonlinear effects both in the bulk of topological photonic lattices and nonlinear dynamics along the edges. So this journal. So to describe such nonlinear generalizations of topological photonic lattices, we developed a formalism based on the nonlinear continuum Dirac model, which in addition to the band gap properties incorporates special dispersion terms and nonlinearity. And based on this model, we predicted that H states can be excited by scattering bulk moving topological solitons from the topological interfaces. This effect was later confirmed experimentally in the group of Professor Zhigang Chen. Also, we discovered the effect of self-steepening for finite H-wave packets which propagate along the domain wall, which is shown here in the middle panel with a gray dashed line. So this effect is seen in growing asymmetry of the shape of the wave packet. And this effect is also responsible for nonlinear stabilization of high intensity H waves. This seems to be quite important because it was overlooked in earlier papers, and topological H states were widely regarded to be destabilized by nonlinear optical effects such as self-focusing. However, we can gain some positive effect from nonlinear instability, and in some cases, bulk modulational stability can be used to extract topological invariant from polarization singularities, which are dynamically formed as a result of instability from uniform steady states. So the other way to extract topological invariance that we proposed is based on Leaky photonic lattices, which can radiate energy into the environment. This scheme can be implemented in integrated waveguide arrays. And in this scheme, we would need to use localized excitation to launch for instance, to launch light in one of the waveguides and measure the complex valued field, that is intensity and phase at the output. But phase retrieval could be a challenging task experimentally. And in our recent development, we also showed that alternatively, methods of machine learning can be used to classify finite topological samples based on limited measurement data and only single intensity image at the output. Considering some historical trend in topological photonics, the efforts were focusing on miniaturization of topological photonic platforms, starting from a magnetized array of ferrite rods in 2009, then arrays of ring resonators and waveguide arrays. But still here, characteristic sizes are much larger than the wavelengths. And finally, topological photonic states can be brought down to the nanoscale in metasurfaces, which may represent arrays of nanoparticles or pattern membranes. Considering closer such two-dimensional systems, such as metasurfaces, we often want to emulate Dirac physics, so that at least in the vicinity of some degeneracies, the spectrum is described by the Dirac Hamiltonians, incorporating Pauli matrices, acting on different degrees of freedom. This is because magneto-optical response is weak and at optical frequencies, and instead of applying magnetic bias, we want to use some engineered symmetries to mix spin degree of freedom. And such designs for nanophotonic topological metasurfaces are often based on honeycomb arrays of resonant particles, such as nanorods or nanoholes in dielectric membranes, with some additional symmetry bricking introduced to open the band gap. So let us consider closer the design based on the deformed honeycomb lattice. We start with unperturbed graphene-like lattice, then we combine 6 nearest neighbors into hexamers and shrink or expand these hexamers. It turns out that at small k vectors, the system can be described as a spin-full Dirac-like Hamiltonian with 2 pseudospins and the mass term. So this is an approximation which is valid only in the vicinity of the K point, and there is a stricter and more correct way to describe this system, but in this talk I would like to use this effective Hamiltonian language. And majority of papers were focused on the domain wall created by inversion of the sign of the mass between the domains of shrunken and expanded hexamers. But we can take a different approach. We can take a adiabatic approach to the design of topological photonic interfaces, and I will show why this can be useful. So if we use a conventional domain, conventional step like mass profile, the H states would be exponentially localized to the interface. And to make the transition region smoother, we can gradually vary the degree of expansion or degree of perturbation introduced to the unit cell across the domain wall from shrinkage to expansion. This will lead to broadening of the H state. And at the same time, the H state spectrally is located above the light line, and it's radiative. So the spatial profile is related to its radiative properties. We developed some theory for this, but in simple terms, as the mode becomes broader, then it becomes more localized in the reciprocal space where our Hamiltonian works better, and it becomes less radiative. So this is perfectly confirmed in simulations. In these band structures, we can see that the quality factor of the mode increases, which is coded here. So we can get an increase of the quality factor from 300 to 6,000. This is how it works in the experiment. Previously, for the step-like profile, the mode doesn't propagate really far. And for adiabatic interface, we can get an increase of propagation distance from 11 microns to almost a half of a millimeter. And at the same time, the mode, we can speculate that this mode becomes less sensitive to isolated defects. To demonstrate this, we fabricated comparable structures. Previously, the mode doesn't even reach the corner. For diabatic interfaces, it reaches and turns. However, this is not probably the way to confine light if this is required for enhanced light matter interactions. The other interesting feature associated with this adiabatic interface is the occurrence of additional doubly degenerate waveguiding modes within the bandgap. They're shown here with dashed lines. Again, the origin can be understood from the Dirac model with non-uniform distribution of the mass in one direction. We can solve the eigenvalue problem with a squared Hamiltonian, and here the red summand explicitly gives us a spin-dependent term. The case with antisymmetric mass distribution is more interesting because it gives rise to the spin-dependent radiative lifetimes of the waveguiding modes. So both in analytical theory based on Dirac models and full wave simulations, and we get that the waveguiding modes are degenerate in frequency. However, they have distinct spatial profiles and radiative lifetime. That was confirmed experimentally. Here, you can see that in the real space imaging, the modes of different spins propagate at different distances. And at the same time, angle resolved reflectivity measurements also show the contrast of visibility depending on the spin of the mode. And this gives us, extends our capabilities for control in the near field and far field. In addition to waveguiding, we can use inhomogeneous patterning in the plane to create the Dirac cavities in metasurfaces for structured light and singular optics applications, such as generation of singular beam. So one way to do this is to apply non-uniform patterning to emulate spin-dependent mass term in Dirac equation, and in this way create trapping potential for light. So we can increase the degree of expansion introduced to the unit cell, moving from the center of the cavity layer by layer. This cavity supports a hierarchy of radiative modes with different topological charges as listed in this table. And in particular, it can radiate azimuthally polarized and radially polarized beams at the same frequency, singular beams. So the beams have don't-like shapes, but through the polarizer, they transform to the lobes. And basically, the measurements for real metasurface perfectly agree with the predicted symmetry of the spatial and angular distribution of the Dirac-like orbitals. So still using the abrupt mass inversion profile, the recent papers reported observation of guided topological H polaritons, which originate from coupling of the structured modes in metasurfaces with excitons or phonons in two-dimensional in van der Waals materials. So this may lead to a new form of Polaritonic transport enriched by functionalities such as bending around sharp corners. But this is insufficient if we would like to control light matter waves on the chip. We would need functionalities beyond waveguiding. And here I come back to this scheme, noting that the similar studies on zero-dimensional trapping of polaritons has been missing. So we propose the design of hybrid polaritonic cavity based on zero-dimensional topological defect in a planar metasurface. So instead of considering the interface between expanded and shrunken hexamers, we create a defect by stitching 3 domains with the same deformation type. So 3 domains, displaced domains of shrunken hexamers meet at the same point, at the core point, producing a co-defect and 3 line defects along the lines emanating from the center. And the metasurface structured in this way is then covered by HBN, which has a phonon resonance at around 7.3 microns in mid-IR. Basically, we couple the lower photonic band in photonic structure with almost non-dispersive phonon vibrations in HBN. And this leads to splitting of the bulk photonic mode into 2 upper and lower polaritonic branches. This slide shows the results for numerically calculated spectra for a hybrid metasurface, where we compare the zigzag domain walls and line defect. Specifically, the H-state dispersion is highlighted here by dotted lines, and the H-states at the zigzag domain walls are almost gapless, while the line defect, the H-states at line defect exhibit much larger band gap, and this band gap accommodates point defect polaritonic mode trapped to the core of the structure and with a relatively large phononic fraction. So having these simulations at hand, we proceeded with fabrication of this metasurface. The thickness of HBN was around 15 nanometers. It was measured by atomic force microscope, and here is an example of the measurement along these red lines connecting the regions of metasurface without and with HBN on top. It clearly shows a jump of around 15 nanometers. So the H-states, the modes of this hybrid metasurface were characterized by real space imaging, and we see here that the one-dimensional and zero-dimensional modes are well confined to the line defect and point defect respectively. Additionally, we confirmed the strong coupling regime, which is seen as splitting of the lower photonic band into 2 polaritonic bands. Next, we characterized the far-field properties of the point defect. The point defect mode exhibits narrow radiation pattern with singularity at normal direction, 3 lobes in directivity with divergence of about 15 degree, and spiral chiral spirals in polarization. So remarkably, the full wave simulations perfectly agree with the vector field maps that can be reconstructed from Dirac model, extended to include phonons with stepwise variation of the mass term and coupling. So that was confirmed experimentally by using the backfocal plane imaging and Stokes polarimetry. So then, to demonstrate some advanced functionality, we designed the trapezoid-shaped cavity, trapezoid-shaped geometry formed by separated line defect and domain wall. So the spin polarized wave of particular helicity can be excited by circular polarized light at the domain wall, can be guided to the corner, to the corner junction, and if driven at the resonant frequency of the point defect, it would lead to the excitation of the polaritonic mode confined to this corner. Yes, this is the optical image of the fabricated structure along with the results for this experiment. So the HBN was placed to cover the whole geometry. And this is how it looks experimentally. We excited the H waves at the middle of the domain wall. And the H states of opposite pseudospins propagate towards the opposite directions. And if the excitation frequency matches the resonant frequency on the point defect, it excites the corner. If it doesn't match the resonant frequency, the excitation only leads to the direction of propagation of the H waves around the corner. And before concluding, I would like to outline the other research directions which we currently pursue. The first one is associated with heterogeneous topological interfaces, which combine two types of perturbations, namely spin hole clustering and valley hole staggering, but now not across the domain wall, but along the domain wall. So they change adiabatically along the domain wall. It could be interpreted as two mass terms and visualized in the complex value plane as phase winding. This topological interfaces enables flipping of pseudospin without back reflection. And we observed the geometric phase associated with rotation of pseudospin in the interference experiment. We believe that this design approach can be useful for integrated quantum photonics applications and designs, new cavity designs for lasing, for instance, at the nanoscale. And the next, the other direction, which is also quite natural, is the interaction-induced topological transitions in hybrid structures. So this is my concluding slide. Basically, I discussed some physics governed by Dirac-like Hamiltonians. It turns out that it can be applied to implement light trapping and radiation shaping in metasurfaces. And we also demonstrated structured phonon polaritons in hybrid metasurfaces. So we believe that this paves the way towards engineering of extended topological networks in the form of extended patterns and polariton shaping and also thermal management at the nanoscale. With this, I thank you for your attention.